Good morning, everyone, and welcome to the engineering design review of the Formula Bharat 2021 electric category. In a typical Formula student event, the engineering design review is hosted by the chief design judge after the finals of the engineering design event as a means of delivering a brief presentation on the pros and cons of each finalist design and key takeaways for improvement. As we have gone virtual this season, the judges have put together key feedback for each finalist in their presentations, supporting documents, QA deliveries, and their vehicles design, which all participants will find helpful. Today's session will be delivered by Claude Rouelle of OptimumG, Pranav Dandekar of WingsEV, and Hugues Marceau of Autonom. Claude will deliver a live feedback of structural and vehicle dynamic aspects, while Pranav and Hugues' recorded delivery will cover the EV powertrain aspects. All three judges have combined feedback provided by the entire design judging team. Please note that there will be no live Q&A collected in this session. The engineering design review of Formula Bharat 2021 electric category is powered by Zukin India. We now invite Claude Rouelle to deliver his design review on the feedback on the structural and vehicle dynamic aspects of the finalist design. Claude, please go ahead.
All right. So Formula Bharat design event feedback of this virtual competition. I have, when I read all your documents, when I listened to your documents, I had basically the same surprise as mostly good and bad that I had when I was listening to you and when I was in real, and I was really having doubt, and I was like, yeah, get out of here. So I'm going to share with you a little bit of the feedback here. So this feedback will be a mix of the design review from the top team as we usually do it before the award ceremony, but it will be also a comment in general about the way the documents were submitted, especially because this is new with this virtual competition and the way the team defended themselves during the Q&A session. There will be some specific comment about cars I judged from Group A, as well as the team from Group B that went in the final. And my observation will be illustrated with picture, graph, and drawing from the team documents. But most of the time, only the team these documents are coming from will recognize them. So I'm not going to say that team, this is a bad design and making a specific comment about that. But I will put on the screen some pictures that only, or most of the time, only the team who created this document will recognize them. First, I need to give a kudo to Kathy and her team of volunteer for the organization of this virtual competition. It was a little bit stressful, but Kathy and her team managed it very well. And I'm very proud and honored to be part of a competition like this one that was successfully organized. Kudos also to all the volunteers, and I do appreciate personally the growing quantitative and qualitative involvement of more and more Indian design judges from the academy and the industry. That's only a good thing for the student and for the industry. Remember, the main goal of this competition is to learn by doing. It's to put yourself in a situation that will be similar to the one you will experience when you will work as an engineer in the industry. It's learning by doing, and Formula Bharat is just doing that. Now, I will start by making a few comments about the engineering design report or the design presentation. First of all, I think this is an excellent idea. Kathy came with this idea of making that in 20 minutes. Should be adopted by other Formula student organizations. I see that there are a few spelling issues. I will correct that. At least as inviting as the 8-page engineering design report that I saw previously. But, and there's a big but, most of the team did cram way too much information in 20 minutes. Example, 20 slides in 80 seconds. I'm not going to tell you it is. I'm not here to point finger. But you need to understand that's not acceptable. 20 slides in 80 seconds. Personally, I'm teaching seminar, and I allow myself at the maximum 1 slide per minute. And here, 3 slides in 3 seconds. Are you kidding me? That's absolutely not make sense. Some of these slides were with flowchart containing as much as 30 elements. I'm going to have you show you an example. I can, of course, stop the video and slowly analyze the content of one specific page, but then defeat the whole purpose of having a 20-minute video. One solution would be to take you by the hand and saying, okay, guys, you cannot make more than 20 or 30 slides in a 20-minute video. But I mean, you should know better. You are not babies anymore. You should maybe learn from the student in charge of the business presentation. Basically, you need to sell your work to the design judge. This is an example of top-down goal. Well, good. It is good. Okay, are you ready for this? That slide lasted 2 seconds. How do you want me to read thing like a complete flowchart in 2 seconds? And it's like, okay, I throw that to you, to the design judge, and it's your problem about the way you are going to swallow that you are going to integrate this information. A few comments continue. On this point of view, one team, Car 08 team DJS did an excellent job. They are not the only one, but they were the best one. They were not too fast and not too slow. Slide and speech speed. It was a quick video at the beginning with the wrong car number, by the way. They had a car 04 and the video was showing 03. And they had a step-by-step introduction of the team goals, the team structure, the timeline, the Gantt chart with readable legends. You will see that sometime there is no legend or the legends are not readable. A budget allocation, process used for effective planning and execution. And at this stage, you only had 2 minutes and you have already a clear vision of the team goal and the team structure. Then we went through each discipline. Ergonomic and chassis driver interface, 4 different drivers. That was smart. I didn't see that in many design presentation, with good illustration of cockpit mock-up, with good pictures and so on. Pedal assembly, safety, seat design, chassis, which included material selection, packaging, torsional stiffness with FEA, impact attenuator, and manufacturing. Boom. That's already a lot of information, and we are only at 5 minutes. So after that, we continue. Vehicle dynamic. First of all, wheelbase and tracks with an S, should be an S here, determination. Packaging, weight distribution, and center of gravity height determination. Tire selection, kinematic decision with a little hiccup, I will explain to you in a minute. Spring and actual bar stiffness and then motion ratio. Linkage and suspension force calculation, very good. The guys who are making the FEA of the chassis and the FEA of the upright will need to know what are the forces and where they are applied, in which direction also. Then the wheel assembly, we are at 7 minute 45, and everything seems simple and complete. Then we switch to brake analysis, caliper design manufacturing. Then you are back to the kinematic with the bump steer. So that should have, it's a little bit out of sequence. That's what I meant. And then steering torque calculation. My friends, steering torque calculation. A team told me that they calculated, they wrote that the steering torque was 48 Newton meter. There is absolutely no driver, even the guy who go to the gym every day, who would be able to turn a steering wheel with a torque of 48 Newton meter. It's nice, it's essential, and it's too often miscalculated. Ignore or miscalculated. And then we start aerodynamics. We are at 9 minutes. Main goal, front wing, rear wing, under tray, bodywork design, weight consideration, aerodynamics disintegration, pitch and yaw analysis, all fall there. And I see many teams in Formula students doing the same mistake. I completely disagree. Look, if your front ride height is 30 millimeter and your rear ride height is 80, you have 50 millimeter difference, correct? Now, if your front ride height is 50 and the rear ride height is 100, in other words, you lift the car up 20 millimeter, you still have the same pitch angle. You still have 50 millimeter difference. So it's the same pitch angle, but I guarantee you it's not the same downforce distribution. You need to produce aeromap with table of aerodynamic characteristic versus front and rear ride height in 2D, and then maybe yaw, steering, and roll angle, which are 3, 4, and 5D map. So a lot of people are giving me downforce and downforce distribution and drag versus ride height and versus pitch. No, that doesn't work. You need to look at ride height and pitch. And that's the way you look at front and rear ride height. And then they spoke of manufacturing, plan for validation process. Wait, we are 10 minutes 30, and at that time we switched to Powertrain and drive. So they had 2 minutes about the team presentation, about 8 minutes 30 on the Powertrain and drive team. It's a good beginning, huh? And we switch to Powertrain. I'm going to accelerate here. They have the goals, the model selection process with a good list of criteria, chain, differential, drive shaft, including FEA, and final drive choice, consideration about weight and manufacturing process. We are at 12 minutes 30. Motor and tractive diagram, battery cell selection and battery pack configuration design, accumulator container design consideration and cell arrangement. We are at 15 minutes. Thermal management for everything, first for accumulator, and then for motor and motor controller, radiator position, packaging, pump selection, accumulator and controller unit packaging. We had 16, 15. And then I will finish with them. Battery management system, high voltage component selection, charger consideration, low voltage, we had 1745, data acquisition start at 1845, and some quick conclusion in the last 15 minutes. This was close to perfect. I don't say that this guy are going to have the maximum points here, but because I may disagree with some of the engineering choice or design process that were made, but the flow and the right balance of information displayed is professional. There was not too much, not too fast, not too little, not too much. A good exam, congratulations. Now, they are not the only one. E01, E02, and E10 teams did a good job too. Now, I'm going to show you things that piss the judges off, really irritate them. Example here. I masked the car number because I don't want to be too offensive. 750 pages of PDF. Seriously, guys, who is going to read that? Even for me, I was looking at suspension, brakes, ergonomic, chassis. That's about 250 pages. And it's literally like you don't care. It's literally like, let's give the judge as much as possible, put that on their lap, and it's their problem to find out what they want to use. That's totally unfair. It's not very smart. Another one. No ability, I had that in the Q&A session, no ability to answer the very simple question. Let me give you that. And what pisses me off is that this information, the question I could use, I could ask are on the internet. You have understood you move the weight distribution forward or backward. 2 teams out of 3 had the wrong answer. You have understood all things being equal, do you increase or decrease the front track? In the garage at 0 kilometers an hour with the car on scales, you turn the steering to the left, what's happening on the right front load that you see on the scale? If you cannot answer that question, you're in deep doo-doo with me. What are the yaw rate and the yaw moment of your car on the skid pad? Which is obvious. If it rains, do you move the brake balance forward, backward? What are the 3 causes of slip angle? And then, unbelievable, define balance, control, and stability, and tell me in which unit you measure them. This is Vehicle Dynamic 101. And if you cannot answer that question, I'm wondering how you designed your car. Does your velocity damping increase or decrease with speed? It's another thing about vehicle dynamic. If you can't answer this basic vehicle dynamic question, you won't go very far with me or any good vehicle dynamic judge, because you will prove to me that you didn't do the indispensable research of information which are available free of charge on the internet. Whatever choice you made on your car design, they won't be justified. And you will prove that you have no or little idea of what you are speaking about. And you started building a home by working on the roof, that's a mistake there, instead of the foundation. You're putting the car before the horse there. Let me show you another one. Incomplete DSS. C factor, steering arm length, no idea where they are. That's unacceptable. Surprise. Never seen a car which had a toe angle bigger than a camber. Maybe you shouldn't know that if you are completely new, but if you know your research, if you make some research, you know that. Long wheelbase, 660. Nobody is building car today which are not close to the minimum wheelbase. Why? Because the cheapest way to make a light car is to make a small car. It has been said by so many different judges all along. It has been written on so many Facebook and forum chat, and seems like nobody care. Now, this is an example of what I found on an engineering design report. It's not an academic course. Excuse me, I'm a design judge in vehicle dynamics. I know what's the mechanical trail, the caster angle. I know that. I don't need to be recalled. You are wasting my time, and you are wasting pages and megabyte of memory of my hard drive. Poor drawing with no dimension. Boom. I mean, it's totally unprofessional. It's unacceptable. Don't worry, I have good things to say also. Let me finish with the bad things, and there's still a lot. Not understanding the ratio between weight distribution and cornering stiffness distribution. Example, you have the same tire front and rear, but you have a weight distribution of 40%. That will not make that car work. When I read this, I stop reading. I know that the guys have no idea what they are speaking about. Worrying about roll center initial position of movement, that's fine. Okay, I have no problem with that. But then no anti-dive and no anti-squat, so the pitch center is on the ground, undetermined. You don't know where it is. I mean, if you are spending a lot of time finding where your roll center position are and should be and where they move, why shouldn't you about your pitch center? You brake and you accelerate. You have longitudinal weight transfer as you have lateral weight transfer. And when you brake, your longitudinal weight transfer is not negligible. So I don't see why you shouldn't care about that more. Steering arm, 42.1 millimeter. That's way too short. It doesn't make sense. You need to use the maximum space that you have in the rim, and you need to design your pride to have a steering arm which is long enough. Otherwise, you're going to pay it in the steering torque and your car will be undrivable. It does not make sense. How come that I have car with 115 millimeter, 115, and some with 42? Some know better what they are doing. That's the other one. They have a so-called constant velocity, which is not true, by the way, on one steering column. If you make your research, and there are some nice video on Facebook and on YouTube, you know that you must have two CV joint and in phase, and that's precise angle. I'm not going to teach you that for the moment. That's not the point. That's another one. This is a Gantt chart. Yeah, no label. So I don't know what's green. I don't know what's yellow. I don't know what's red. And sometimes I have worse. I have labels that I cannot read. I need to zoom really big time to see. And don't tell me that here in the gray part and there, you didn't have the room to put some legend and explanation of what color represent what. That's an example here. I have two problems here. Number one, there is no units. Okay. Is it millimeter? Is it Newton? Is it Newton meter? And then look at this angle here. I look at the pitch angle with 1, 2, 3, 4, 5, 6 decimal after the point. Why do we need such an accuracy? Why is that important? And I've seen that in so many other table, and I'm going to show you another one soon. That is another one. A damper dyno that do not make sense. I never have seen a damper dyno. First of all, they told me that the positive is rebound. Okay, I can buy that, but usually that's not the way it works. But then you have so much rebound on one side and nothing. I mean, how do you publish that? You should know from your literature that nobody has ever invented a damper like that. That car would be awful to drive. It does not make sense. How do you dare to publish something like this? Look at that, another one. Anti-dive and anti-squat on the DSS, 10%, but 5 point, and no, because there is nothing here, no anti-squat, but 5.8 at 10.2 on the engineering design report. So DSS and EDR data do not match. Did somebody read the document? That's another thing that I have a little bit of a problem, and that's typical Indian here. Senior, look at the bottom of the flow chart, senior engineer and junior engineer. If I have a problem with this, if the student is gone, even in his first year, give him more responsibility. No, you need a good guy to decide if the young engineer is good. But you have leaders and follower. I don't accept this thing. That's typical from India. I don't see that's happening. Japan also, but okay, no more comment in there. That's another one. These people were showing me the front right eye at 80 millimeter, and then the downforce, drag front downforce, re-downforce, coefficient of drag, and coefficient of lift at 60 kilometers an hour. And then 30, 40, 60, 40, 50, 60, 80. That's the rear right eye. How do I know that? How do I know that the ideal right eye is 70 millimeters? How do I know that's the rear? It's written nowhere. It's not written on the Excel spreadsheet. And it's not written in the comment. Look at that. Considering the CL value as safety issue, we decide to maintain the right eye as 70 millimeters from the ground. Which one? The front or the rear? I guess it's the rear because the front is mentioned as 70. Let's be serious, guys. You need to have somebody else reading your stuff there. This is an example that is not from a Formula student. That is an example of front and rear right eye, and at 240 kilometers an hour, one by. It's a real race car. But you have front and rear right eye there, and that's the downforce distribution, for example. That's something you can do. That's another one that a team showed me, and I like this because it's sexy and so on, but it's not useful. And I'm going to tell you why. It's not a bad idea to present the things, but first of all, this car isn't drivable because if you have between 50 and 58% of downforce distribution, when the car brake, accelerate, and so on, nobody can drive that car. I would prefer to see a 2.5 mat. And then that I don't get it. Somebody has to explain to me how you can have negative right eye, because you go from 20 to minus 30 and from 20 to minus 30. Maybe it's variation of the right eye starting from an initial position, but I don't know what it is. So maybe it's relative value. Anyway, I cannot read and I cannot use this. That's the other one. This is car 01. I have told them for so many, that's not the picture of that car. I didn't take a picture of car 01 here. I'm very, very clear about that. Z-bar is a bad design. I never have been a fan of this. And the number one reason for that is that when you don't have the anti-roll bar drooping in the plane of the rocker, this is a simple bad big source of compliance. It's a bad design. You are not going to convince me of anything else. And I've been telling that to Orion Racing for so many years, and I don't know, they don't seem to listen. In any case, the design of Orion from 2020, 2019, 2018, that's barely practically the same. Now let's make some good thing here. That, for example, I really like this. Center of gravity sensitivity, depending the driver acclimated. So you give a 100 to the driver, and the front bell crank is peanuts compared to the rest. That is a nice way to present things. I really like that. This is another one. I mask the input, but you have sensitive for acceleration, autocross, kick pad, battery consumption dependence. And things like, of course, center of gravity and weight and so on are there. It's up to you to do that. And the reason why I decided to blank this is because in India, the people like to copy without understanding. And that's why I said, that's your problem. You need to find. But this is a nice way to present things. People are using the yaw moment versus acceleration, which allow you to determine what's the grip, the balance, the control, and the stability sensitivities. Let me show you something which is not from Formula Student. That's an OptimumG stuff. You have example here, the grip and the balance for different characteristic of the car, like the rear spring, the rear anterior bar, and so on. And you have this little bar, and each bar corresponds to a different pressure distribution, 1.6, 1.6 bar, 1.6, 1.9 front rear, 1.9, 1.6, 1.9, 1.9. That's an example for grip, balance, control, and stability. This is a suggestion I encourage you to do, because it will help you to tune your car in a very, very fast and understandable fashion. Chassis torsional stiffness distribution. Not a lot of teams are doing that. If you have 2,000 Newton meter per degree, and you have chewing gum on the front and something super stiff on the rear, or the other way around, it's still 2,000 Newton meter per degree, but I guarantee you that on the racetrack, it's not going to be the same. So I encourage you people to push that for that. That's, for example, I mask, here the blue stuff, but I really like the sensitivity study about tire pressure, anti-roll bar, ride height, and so on. Which spring is the best for acceleration, or which anti-roll bar is the best, or what's the ideal aerodynamic balance for acceleration, skid pad, autocross endurance. Good, love that, fantastic, good job. I like that. People are practical. They are not only theoretical. They use their knowledge there. And then there was one team that I really like. They were starting to do transient simulation with a controller, and I think that's very, very good. I wish there would be more explanation, because putting your MATLAB flowchart, that's good, but I need to have your equation in writing. Sensitivity study, that's good, excellent. Now, I have to ask you, it's impressive. Do you need so much precision? Look at that. You have here the coordinate of the center of gravity with an accuracy of 1/10 of 1 micron. I don't understand, so it's not necessary. Conclusion. I'm coming to the end of this. First of all, it seems that there were a lot of progressment on the electrical power and drivetrain, and maybe vehicle dynamic has been left a little bit on the side. It's your decision. I don't blame you. It's use of resources, up to you to decide. In fact, many 2020 car resemble strangely to the 18 and 19 car. I need to correct that. Maybe the time installation due to the coronavirus could have been used a little bit better for simulation. Too much info crapped in the EDR, PDF, PowerPoint presentation of video. There's no need to put so many information. Put the right amount at the right time in the right sequence. Stupid spelling mistakes. like mine, I have to recognize, and inconsistencies between design specification sheet and EDR. And I have your document being revised, included by a non-formula student, student or a teacher. That's my advice, and force some team back to the basic. And what is, again, very irritating is that most of this info that need is available online. I will finish by my biggest wish that I have for 2021, and it's this one. Whether it's in India or in Germany or in Spain or in Austria or Russia or China or whatever, I wish that in 2020, I'm going to be able to advise and judge you face to face because I miss the interaction. And I have to say that, again, that I'm very critical. I'm not an easy guy. I'm pretty demanding, but here's the reality. With all the mess that we are going through, and I'm polite, you guys have done a fantastic job with the virtual design presentation. And once again, it's a pleasure to work with you. It always will be. And thank you for Kathy and her team to organize this competition. And I hope face-to-face, big hug, high five, that we can give each other next year. Thank you, guys.
Claude, thank you for your presentation. I'm sure the participants found this very helpful towards their design considerations for this next season. You have a good evening, or a good night, actually. Right, up next are 2 recordings covering feedback on the electric vehicle powertrain design of the finalists. First up is the feedback provided by Pranav Dandekar of WingsEV.
My name is Pranav Dandekar. I'm one of the judges for the Formula Bharat electric vehicle engineering design panel. And so now that the competition has concluded, we wanted to do sort of a review of the design to see if there are any sort of high-level messages that we can convey to you all as you prepare for next year, right? Sort of my background. In my day job, I am building an electric vehicle. I'm co-founder and CEO of a startup called WingsEV. We're building a radically new vehicle for urban commutes in India. And so many of the issues that you face, your teams face in building the competition vehicle, those are issues that we've dealt with in a slightly different context. And so what I want to do in this design review is, instead of going over each individual team or individual finalists' presentations or critiquing them, I want to talk about this high-level topic, which I think is very central and very important, of powertrain sizing and component selection, right? And what I want to do was, first of all, because we've done this for the vehicle, I'm building, and secondly, because I've seen a number of various approaches, and there's always a few things that felt like they were missing in the reports and analyses that teams submit to us. So I thought it would be helpful if we walk through that, and in the process we will use some of the finalists' designs and decisions and analyses as examples, right? So in my mind, there is a reason why this topic is sort of very important, right? And let me sort of step back all the way to the highest level, right? Which is that the goal of this competition, even though it's a competition, the number one goal of this competition is for you to learn, and you to learn by doing. And the actual winning or losing is only sort of secondary, right? So you're competing, but that's not the main goal. Is not to win. The main goal is to learn. And when we as judges are looking for learnings, what we're looking for is consistency of reasoning, in the sense that, can you articulate what your goal was? What is it that you set out to do? And do all your subsequent analyses and subsequent decisions, are they consistent with your goals, right? And so that applies as well to powertrain component sizing and selection, right? And so the way I would like to sort of structure this is to say, well, your number one goal, step one in this is to set measurable performance goals or targets for each event or whatever events you care about, right? So, for example, Team E13 Ojas, right? They said, well, one of our goals is to complete acceleration event within 5 seconds, right? Team Octane, which is I think E02, they said, well, we would like to achieve 1.2 G longitudinal acceleration, right? So first of all, start with some measurable goals or targets, right? They may be for the endurance event, for skid pad, for acceleration, and so on. But they have to be specified in those measurable terms, right? Now, once you have these sort of performance goals, then the question is, what do those goals, what kind of requirements do they impose on your powertrain, right? So as an example, imagine if you had an endurance goal of completing a single lap in some amount of time, right? Now, if you had that, then the next natural thing to do is to say, well, if I have to if this vehicle of this weight and so on has to complete this lap in this amount of time, what does it mean for the torque and the RPM that the vehicle has to provide, right? And so a number of things. So, for example, I think this is a plot from the E13 team also on the right, and on the left, this is a nice heat map along the track from E15, I think, Stallion. And so I think, but what I did not see, I think, in any presentation, in any analysis, was plotting these two numbers on the same plot, on a single plot, where you plot both the RPM required and the torque required to complete your lap, right, in the amount of time that you set as the goal in step one, right? And the reason for this is that these two numbers, the torque and RPM, as a function of time, those will determine the subsequent selection of your powertrain, right, which is motor and so on. And so, right, and so now let's talk about designing the motor, right? So now if you have a figure of what torque you need and what RPM you need, then the question is, well, what does your motor and gearbox design have to look like in order to deliver the required torque at the required RPM at all times, right? So often in these presentations or your reports, we saw that there was a lot of discussion of peak torque. Peak torque was like one of the criteria for selecting motors or was specified everywhere, right? In my mind, peak torque is not nearly as important as saying, well, first of all, now that you have a plot where you have both torque and RPM on the same curve as a function of, on the same plot as a function of time, you should be able to overlay for any given motor plus gearbox how much torque that motor plus gearbox can deliver at every RPM, at every point in time, right? And the idea should be that the motor plus gearbox that you design or you select should at all points have more torque available than what is required, right? So number one, it should have more torque available than what is required. Two, there should be a margin of safety or some sort of margin. That margin could be 10%, 15%, whatever it is, but you should be able to justify that margin, right? For example, that margin cannot be 100%, right? I mean, you shouldn't deliver, or you shouldn't have available twice as much torque as is required at all times, right? That would be the definition of sort of a over-designed or oversized powertrain, right? Which we saw a lot of also, including in the finalists, right? So everything that I'm describing here, the finalists did slightly better than other teams, but the finalists in some sense were also guilty of sort of over-designing the powertrain, just saying, let me just find the most powerful motor and just throw it at the problem, right? And I'll describe some of the problems that happened because of that. So the idea is that you have the motor plus gearbox, right? And they combined deliver some amount of torque at the wheel, and that available torque that they can deliver should be greater than the torque that is required as per your own calculations. Right? Now, once you do that, right? Now let's talk about the choice of motor, right? Now the main thing to remember is you're not selecting the motor first and then designing the gearbox later necessarily, right? The two things have to go together, because it's possible to essentially go with a smaller motor with a higher ratio gearbox, right? Which might turn out to be a better selection than a more powerful or more higher torque motor with a lower ratio gear, and we will see, right? So with motor selection, like I said, peak torque or peak power is not the most important spec, even though often that's what we saw in the reports and being specified again and again. In my mind, other important specs include things like power to weight ratio, right? You want a motor that is powerful for the weight it has, right? One of your goals should be to reduce the weight of the vehicle, and you don't want a very heavy motor. Right? Another important criteria for choice of motor is what kind of cooling does it require. Cooling will make the motor sort of assembly more complex. Cooling will also suck up more energy, right? So if the motor doesn't require cooling or is air cooled versus water cooled, these are things that are important. Two other technical things that are important. What's the voltage of the motor, right? And the reason the voltage of the motor matters is there's a trade-off between high voltage, low current powertrain versus a low voltage, high current powertrain, right? And this is a question that we asked all of the finalists as whether they understood the difference and what were the trade-offs and why they chose what they chose, right? And so the voltage matters. Another thing that matters is the torque constant. The torque constant is the amount of torque the motor can deliver per unit current, right? And you want a motor with a higher torque constant. Everything else being equal. Because if a motor has a high torque constant, then the same torque can be delivered by lower current. And if the current is low, that means your I square R losses are even lower, and so on. Right? Because losses are proportional to square of the current. And so the reason these things are important is because once you fix the motor, that fixes the battery pack voltage and it fixes the battery pack current rating, right? Because the motor runs at a specific voltage, the battery pack has to provide that voltage. And the motor has current requirements, both continuous and peak, and the battery pack must be able to move, right? And so it's not prudent in my mind necessarily to choose a motor, to choose just the most powerful motor you can afford, right? These other things matter, and I haven't seen enough analysis of things like cooling, right, or things like voltage, right? I mean, I didn't see teams analyzing sort of lower voltage motor versus higher voltage motor necessarily. Some teams did, and some of them were in the finals, but these things matter. In general, as a rule of thumb, for the kinds of power you're looking for, it's probably most prudent to choose a voltage, a motor that's say somewhere between 200 to 400 volts. Some of the teams, including some of the finalists, were much higher, including at like 530 volts and so on. And that wasn't necessarily, that seemed over-designed in some ways. On the other hand, there were also some finalists that had 72 volt powertrains. I think Octane has a 72 volt powertrain. And there are some fundamental problems with it in the sense of if you have a low voltage, high current powertrain, then there is a whole bunch of consequences of that, which you have to be very aware of, right? And so, so that's something to keep in mind. And in general, it feels to me, given how sort of, it seems like things are over-sized or over-designed, it might be best to use a motor that is high voltage, say somewhere between 200 and 400 volts, but slightly lower power, right? But it's coupled with a higher gear ratio, right? Or at a minimum, you should analyze this possibility. Can we get a small motor that has lower torque, coupled with a high gear ratio? And that small motor, because it's small, needs lower voltage, lower current, and that means lower costs and lower losses and higher efficiency, right? So that's something that I think is well worth analyzing, and that's something we would like to see as an analysis in your decision to choose or not choose a given motor. Now, once your motor is fixed, right, that sort of determines some of the specifications of your battery pack, your accumulator, right? So, for example, the motor voltage determines the battery pack nominal voltage. If your motor, will deliver that a certain amount of power at say 400 volts, so then your accumulator has to be rated for 400 volts, right? Now, once you fix the voltage, you know from your lap simulations the energy required per lap or energy required for any of the events, right? And so then that determines the total energy of the pack, right? Again, there has to be some margin of safety. And again, we would like to see you defend or justify that margin of safety. The margin of safety doesn't have to be 100%, right? The reason, going back to sort of the motor constant or the torque constant, right, is if you can find a motor that, everything else being equal, has a higher torque constant, that means that to deliver the same torque, the motor will draw lower current. And if it draws less current, then it puts less, smaller requirements on the battery, right? And so there is this trade-off between, given your energy, given your voltage, you could either build a small pack with high C rating cells, which is what we saw most of the finalists do. They used cells from Melasta or other places which had continuous ratings of 10C or peak ratings of up to 15C, right? Which I imagine are much more expensive, right? The other option is to build a battery pack that's slightly larger in capacity in terms of ampere hour, but has lower C rated cells, so only maybe 3C or 5C rated cells. And this is a cost trade-off, right? So you could, depending on whether the high C rating cells are more or less expensive, you should decide which to use, and that should be in the report, right? So all of these decisions are essentially about why, right? Why did you choose a motor? Why did you choose a cell, and so on? And all these have to be justified in the report or in the presentation. The one thing to keep in mind is a couple of the teams in the finals and a number of other teams also had used small cylindrical cells, and then they were doing spot welding of those to put them into modules and so on. And that feels like, again, over-engineered or need less. Compared to that, if you use pouch or prismatic cells that are slightly bigger in capacity, then either you could just build a 1P pack, or you could build a pack with a smaller number of Ps, in parallel chains, but which are easier to deal with. Potentially, you can just bolt the bus bars on them, and so you don't have to worry about spot welding, things like that. So on balance, it might be easier to work with a small number of large cells rather than a large number of small cells, right? And then I think finally a couple other points about the battery pack design. One is about thermal and the other is about BMS, right? So we saw a number of teams had skipped the thermal analysis of battery packs, and they were penalized for that, right? But even the teams that did thermal analysis, they never quite explained why thermal analysis was needed in the first place, right? And so ideally, if you're using a higher voltage system, then you don't need a lot of current. So start with a motor that's not very powerful, but it is higher voltage. So your current is lower. If your current is lower, your I2R losses are lower. If your I2R losses are lower, then you may not need active cooling. And so, first of all, your thermal analysis should describe why you even need cooling. Secondly, which is even more important, is there are ways of doing passive cooling in some clever ways, which should be analyzed or explored before you jump to some heavy-duty active cooling. In some cases, we saw teams using 10 fans, right, to do the cooling and consuming something like 80 to 100 watts in the process, right? So there are things around phase change materials. You can consider using thermal pads or gels. You can consider redirecting some of the ambient air into the battery pack in some ways to sort of passive cooling without actually having to build an entire system of fans and so on, right? The last point was about the BMS used in the battery pack, right? So I think in the finals, there was probably even a distribution of teams that had written their own BMS versus teams that had bought PMSs. I know that even as late as 2 or 3 years ago, there weren't a lot of BMSs available in India. And so buying off-the-shelf BMS might not have been a valid option, say 2 years ago, but that has changed rapidly. And so at a minimum, if you're going to use your own BMS, it needs some justification as to why you're writing that code, right? And it's useful to sort of realize that everything that you do from scratch that is custom done, there's a higher probability of failure. So if you want to make the system more reliable and you want to make it sort of easier to plug and play, then it's better to go with production grade components that are built by other companies that you can just buy and plug in, right? As opposed to building things from scratch, where then you have to debug and it just like makes the system much more error prone. So if you're going to build your own BMS, you should have sort of good reasons to do that, right? And so I think if you start with your high level goals, break them down into requirements on your powertrain, and then break those requirements down into requirements in torque and voltage and current and so on, which then leads to selection of motor and then selection of battery pack and so on. This type of a systematic approach, if you can first follow it and secondly explain it in your presentation and in your report and so on, that I think would go a long way. First of all, for you to build a vehicle that is appropriately sized and appropriately sort of selected for, and then also be able to explain and defend those, right? So I hope this was somewhat useful in helping you plan for next year. This is all I had, and Godspeed, and we'll see you next year.
Next and final recorded feedback on the EV powertrain is provided by you, Marceau of Autonom.
So hi, I'm Hugues Marceau. I'm a judge in the electrical powertrain subsection of Formula Bharat 2021. I'm an electrical engineer, turned out battery scientist, turned out entrepreneur. I have a company, we're making battery backups for the telecom industry. And I'm very happy to be among you and to evaluate your teams. So I'm a Formula SE alumnus. I founded a team in, I think, 2009 and built 4 cars with a couple of friends. It was a great learning experience. One thing that you have to take away out of this is, and there will be winners that will be announced, but like my team, it never won anything, well, barely. But I still consider myself a winner because I won what I learned. And usually the worst teams learn the most. So keep that in mind, that everybody is a winner. I know it sounds really really pink and beautiful, but it's the truth. Like, I'm really proud of you guys. Keep up with the good work, and keep in mind that your learning is proportional to your work. So the more you work, the more you learn. This is the engineering design review of the electric subsystem of Orion Racing India Electric team. Orion had a great battery thermal management system, and they used silicon pads to improve the cycle life of their battery because it reduced the mechanical constraints on the pouch cells they were using. Also, they properly explained to us why their thermal management was designed by use of simulations and calculations. One thing they need to work on is, instead of using limited designs, just like saying like, oh, we have a choice between this motor of 80 kilowatt and this motor of 80 kilowatt, it would be better if they justify what is the best compromise in power. Like, maybe it would be 82 kilowatt, and then to take into considerations the limitations of the choice they made. Hi, this is the engineering design review of the electrical subsection of Octane Racing Electric team. Octane had a really good design methodology. I'm really impressed. They followed a strict protocol. Something that needs to be worked on is the lack of thermal management in the accumulator container. Like I haven't seen proper simulations and calculations. Generally speaking, when they show simulation results without explaining the parameters, it does not prove us that they understand properly that the simulation has been done right. So this is something I would like to see next year. This is the electrical design review of the electrical subsection of the team Kratos Racing Electric. You guys had the best presentation among all teams. Like, I'm really impressed. Hats off to you. In regard of the component selection, it was very detailed. All the choices were explained in matrix. I really liked it. One thing that I would like to see better for next year is that I would like you to understand the intent behind the rules and try to make a design accordingly. I'll just give you an example, but it happened at some other occasions. So, like in the rules, there is a, like it says that the thermistor needs to be placed to measure the battery temperature. So if it's placed near the battery, if it touches the battery, it will pick up the temperature of the battery. But if it's a little bit further away and there's a lot of airflow, it will measure the temperature of the air more of the temperature of the battery. So try to understand better the intent of the rules and it will greatly improve your design. This is the electrical design review of the electrical subsection of DJS Racing Electric. You guys have one of the best design. I'm really proud of you guys. However, we haven't been able to score you optimally because we don't have the right proofs that you guys are getting it. So this is what you need to work on. Like show calculations, show simulations, show processes, and then your score will get better next year. This is the electrical design review of the electrical subsection of IIT Bombay Racing team. So this team showed the best understanding of compromises between the subsections. And this is really the kind of understanding that I want and that I love when there is like a bigger battery pack to compensate for more aero drag. This is where the best team shines. To score better, I would like to see more thermal simulations result, especially in the accumulator container and motor, showing test result, validation, calculations. It needs to be done to level up. So this is the engineering design review of the electrical subsection of Accelerator Formula Racing. This team is definitely one of the best team in designs. They showed us right design calculations and simulations. An area that I would like to see improved is again in accumulator thermal management. There was lack of documentation. And where your team didn't shine the most is in the Q&A. Maybe because the presentation was a little bit too big and there were too many slides, you team members haven't been able to answer questions right. Try to improve this kind of presentation and you'll do better next year. This is the engineering design review of the electrical subsection of Team Ojas. Great work, team. A common flaw of many teams is the thermal management that is overlooked. But one area that your team also overlooked is in regard of efficiency. I would like you to well, showcase that you understand the compromise that you guys are taking or not in efficiency. Hi, this is the engineering design review of the electrical subsection of IIT Roorkee Motorsports. This team had a very good low voltage system, and they made up Simulink models to justify their component selection. Like, it was really good, but it needs to be better explained on how the Simulink model works, and well, to justify better the results. So here are some takeaways that I would like you teams to keep in mind for next year. So first takeaway, the engineering design finals is not about your design, but actually about the process and the understanding underneath. Judges, like myself, we don't care, we're not supposed to care about if you did it right. What we're looking for is, if you do it wrong, maybe you have a great explanation on why you do it wrong. And like, this is what we are looking for. We're aware that budgets are not the same for every team, and like, sometimes to do it right, it costs a lot more. So don't feel disadvantaged by your budget. Another takeaway is that you guys need to keep in mind that you are making a race car. To go fast, the powertrain of a race car shall be light, compact, efficient, coherent with the rest of the race car. So let's say you have a big aero package, you cannot have a small powertrain because it will require more energy, more power to go fast. The powertrain needs to be reliable, and to showcase that it's reliable, it needs to be simple and tested, and it needs to be grippy. So this is an area where there's interface with suspension and aero and many other subsystems, but like a very powerful race car would need well, more wheels to be driven to maximize their grip. Keep that in mind. And like, the more powerful is the car, the more the more power it needs to transfer to the road. So now, in regards of, I'll give you things that help you demonstrate to me that you understand. So there is, in system engineering, something called the V diagram. It's a process that is used commonly to to showcase to engineering systems properly. And using this V diagram allows a team to communicate that you understand what needs to be done. So I recommend all the teams to take a look at the wiki page of V diagrams in system engineering. A quick summary is that teams shall start by setting up goals, having high-level requirements, and then make hand calculations of how it should be done. And then you make a design, you test, you simulate it, and then you iterate, and then you validate like that you met your goals. So this is the basics of the V diagram. It's often overlooked among the teams, and it would allow us judges to score you better, because it would show us that you understand or not what you're doing. And so something that does not show us if you understand or not is, just using the data sheet or tables that are in components that you buy. A common example is with a fusing. If you buy a 100 amps fuse, it will not blow at 125. It will blow according to how much current is drawn. After a certain period of time. So the intent of a fusing is a last resort to protect your wires and components. Fusing is very tricky, but the fact that the teams overlook it means that the teams often don't understand like how well the intent of the fusing. Another thing that shows a lack of understanding is adding features to a car. So to go fast, the car does not need to have a Kalman filter to estimate the state of health of a battery or like active balancing. These are features that if added to a car, it shows that you don't understand what it's required to go fast. So be very, very careful of adding these kind of features that you think that would improve your design, but that just give a negative impression of what you guys are doing. Lastly, a simulation does not show us judges that you understand what you're doing. It just shows that you're able to do a simulation. So try to counter verify a simulation with a hand calculation, and so that would allow you teams to score much better. Overall, great job. I'm very impressed by what you guys have been doing. I'm sure that like I envision very high success for you all. Bye. So hats off to all of you and good luck.
And that wraps up the engineering design review of the Formula Bharat 2021 electric category powered by Zook in India. We hope you have found this feedback helpful in preparing for the upcoming season. Before you leave, if you like our content, be sure to subscribe to the Formula Bharat YouTube channel for updates on future live events on the channel. See you this evening at 7 p.m. for the award ceremony for the Formula Bharat 2021 electric category. Have a good afternoon.